developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, I'm Alejandro Strachan, Professor of Materials Engineering here at Purdue University and the principal investigator of this effort. I'd like to start by thanking the AFRL Hub for their support to this exciting project. So when engineers are designing new propellants, they worry about performance characteristics like ballistic properties like burning rates. But they also have to worry about mechanical properties. A crack in a propellant could have catastrophic consequences. So in this project, we're extending our prior work where we have developed ballistic models to include mechanical properties as well. Our ultimate objective is to provide tools to formulators so that they can accelerate the design of new materials.
Essentially, what we're doing is taking thousands of experimental data sets in the open literature that relate solid propellant composition and microstructure to their mechanical properties, then using machine learning to model that relationship. Mechanical properties here are going to be things like ultimate stress, ultimate strain, yield stress, and Young's modulus. We will also be building a visual app so that these tools can actually be used by researchers and formulators without extensive knowledge of modeling or Python coding.
Determining the strength of a new solid propellant formulation is an important part of its characterization. However, to find these values for a new formulation requires hundreds of grams of material, as well as the usage of in-demand mixing and testing hardware. Predictive models can be used to help screen potential new formulations so that we test fewer poor performers. These models can also be used to quickly give new formulators an intuition on what combinations of chemicals result in good, strong propellants. That kind of quick prediction tool didn't exist before, and it's a valuable addition to AFRL's toolbox.
One of the most important aspects of the first phase of our project is the curation of our mechanical properties database. It is very important to discover input errors and inconsistencies that could affect our models. In other fields of material science, chemistry, and biology, there are professionally curated databases, often behind a paywall. That's not the case in energetics materials, so we need to curate our database to make sure we start our modeling effort on solid ground.
Through this effort, we are overhauling a database of around 1,300 mechanical properties test results that were initially collected for the DARPA RIDE program. These 1,300 test results cover different testing conditions for over 500 unique formulations acquired from about 100 different sources, including in-house testing at Purdue. These results correlate the propellant's chemical composition and casting process to their ultimate tensile strength and strain, as well as Young's modulus, yield properties, hardness testing, DMA results, and indentation testing when reported. However, this data was collected by around a dozen different researchers with little oversight and no automated database validation, so there are inevitably some inconsistencies and input errors in the data as is. The work that we've been doing involves using text processing and statistical methods to find areas of confusion or significant outliers in the data. We've gone through and fixed hundreds of incorrectly entered or incorrectly reported values, dozens of chemical aliases and misspellings, as well as standardizing several text descriptors, such as the tensile test, specimen shape designation, and others. We have experience in finding these errors due to similar work for a burning rate database as part of the DARPA RIDE program, and we're confident that our efforts are going to result in a much better final product for AFRL.
The results from our modeling efforts have been very promising so far, and we're happy to share those results with researchers who can benefit from it. In addition, we're excited to extend our models to new properties and improve their accuracy. The last leg of the effort is working on a graphical interface that will turn our model into a fully fledged formulator assistant.
The other component of our final product for the first increment is a set of trained models that can predict the propellant's mechanical properties from its constituents and a given test condition. These models are able to give predictions for not only AP composite propellants, but also double-base propellants and gumstock surrogates. We're able to take into account testing temperature, strain rate, and specimen size with our models. And importantly, all of these features and models have been incorporated into a graphical user interface so that they're easily accessible by anyone cleared to access them.